Hi there, my name is Gavin and this is my Lab 5 submission video for CPE 316. So in this video I'm going to demonstrate pretty much all of the different tasks and I'm going to be pausing and restarting the video as I go because there are some times where I'll need to um, wire up the board in a different way. This is going to be a bit different than the other demonstration videos, but it won't look that different to you. So, okay, let's get started with the first one. So first, we were tasked with creating a three-wave function generator that will have sine waves, triangular waves, and sawtooth waveforms. And they're all going to be 100 hertz. And we're just going to take a look on, I have a logic analyzer here, which is going to serve as my oscilloscope. And we're just going to take a look at its output and see if turning this potentiometer will give us different waveforms. Okay, so ignore the LCD here. It says something, but it's just because it's a relic from a previous program, so don't worry about it. I didn't do anything with the LCD in this program. So here I am in Logic, and we'll add the measurements later. So I'm just going to go ahead and get started. I've turned this all the way to the left, this potentiometer, and I'm just going to hit run. And as you can see, we're getting some nice triangle waves. I'm going to turn this, I'm going to click play again, and I'm going to turn it a little bit, and then we should, okay, yeah, now we'll see that we're getting sawtooth waves, and you'll see like there's this line coming down, but that's just because we're dropping from up here, which is like almost 3.3 to 0. On the oscilloscope, you don't see that, so I'm guessing it's just like a function of me using this logic analyzer, but also it does make sense because you are dropping from 3.3 to 0. So anyways, this is different than triangle wave. This is the sawtooth. Okay, I'm going to hit play again, and of course we're still doing sawtooth, and I'm going to keep turning this. And okay, now we've got some nice sine waves. And again, if you notice that all of these have the same period and same frequency by extension, they all kind of look like the same size. So I'm going to run through the whole thing again. We're at sine right now, and then I'm going to turn it down. There's sawtooth, and there's triangle. And again, they're all the same period and frequency. So unfortunately, the logic analyzer doesn't stop because that's not really what it's for. So it's kind of hard to just see as you go, but I can stop it and you can see it. Anyways, to prove to you that it's 100 hertz, I'm going to add a measurement. I'm going to measure the period or frequency, of this. Okay, so, okay, well, usually that works, but, okay, fine. Let me trash this. Usually it works if I just do that, but not today for some reason, so that's okay. I'll just do a big portion. Oh, I know what I did. I totally measured the wrong thing. Okay, there we go, 100 hertz. And then we have a period of about 10 milliseconds. And then, let's see, if I go to, I don't know if I kept my other waveforms on here. Oh, that's it, cool. So now here's where in the sawtooth, I'm going to do this one. Let's start from here. And go to there, give it some extra room. And 100 hertz again, and a period of 9.9 milliseconds, almost 10. And then let's go back to sine. Okay, and there's that. And we get about 96. So sine is just a little different. I noticed this when I was doing on this oscilloscope too, that it's a little less than 100, but it's very close. And we also have a period of around 10 milliseconds. So that's great. So what this tells me is that, yes, I was able to get the right frequency, and we have this potentiometer controlling the different different waveforms that someone will choose. And that's it for that first task. Okay. So now let's do this next one. Okay, so here I'm going to pause the video because I need to do a quick rewiring, so I'll be right back. Okay, so here we are, we're back, and now I'm going to demonstrate task 2. Where else my document? There we go. Okay, so in task 2, we are using the potentiometer to control the duty cycle of a wave that we'll again view on the logic analyzer. And we're also outputting the duty cycle as a floating point number on the LCD. So as you can see, we're just starting at 62. I just had it set to that, I don't know, because that's where the potentiometer is now. But I am going to go to here, my logic analyzer, and we'll start from 0, so you can just see what's going on. And we're just going to check and make sure that the duty cycle is working. Okay, so that's 0, and then I'm going to slowly turn it up. You're going to see we've got a little, we're slowly changing the duty cycle. You can see it getting bigger. I guess harder to see as we go faster, but, as the duty cycle increases. So I'll stop maybe right now. And you can see that's 39%. Then we go a bit bigger. Okay, that's 79%. Wow. Okay. And then, okay, now I'm at the max. So you can't actually go to 100, but that is 98%. And that totally makes sense, right? And that's pretty much what it would look like on the oscilloscope as well. Just a bit different. But that's kind of the gist of what this task was about. It was just about using the potentiometer to control the duty cycle, to output it on the LCD, and then also to double check with your logic analyzer or oscilloscope. Okay, so now we are going to, this part's actually super easy to demonstrate. So all you have to do now is just take a look at the board, at this LED right here, the onboard LED, and hopefully you can see it. Yes, you can. Good. So I'm going to start from 0. And you'll notice it's off. But as I continue twisting this and increasing the duty cycle, wow, look at that. It is actually increasing in brightness. So you might have a hard time seeing it. Let me move this camera down here, because the LED is kind of small. So we're at 0 right now, but I'm going to keep increasing it, and you'll notice we kind of go from dim to brighter, and now we're at the brightest spot at 98% duty cycle. So what this is showing is simply just that the duty cycle, or the wave we're outputting using pulse width modulation, is able to control the brightness of this LED, which is pretty cool. And depending on the duty cycle, it's going to be less. I'm just using PA5 because our PWM is actually connected to PA5, so that makes it pretty easy. You don't even have to connect another LED. And again, the LED is connected to PA5, so they're already linked, so which is pretty nice. Okay, so for the next task, we were tasked with designing an analog interface to, using the universal op amp to switch a negative 0.5 volt to a positive 0.5 volt wave to this positive 0.5 to a 3 volt wave. So I'm not going to go super in depth with this because you'll see my calculations within my demonstration. However, I will open this in LG Spice for you to see. So here is the schematic. We have our op amp right here, and then we have the 3 calculated resistor values, and this is also a calculated resistor value. I should have said that too, but this is the feedback for the universal op amp. Okay, so let me just run this real quick, and I'm going to probe right here, and right here. And you'll see the green wave is our initial wave. It's this sine wave that goes from about around 0.5, and you can see that down in the corner if you want to take a look. 0.5 to, or negative 0.5, let me say. Negative 0.5 to positive 0.5. And then this blue wave is where I grabbed from right here. This is going to go from 0.5 positive to, of course, you can already tell, 3 volts. So that's that. And of course, you'll take a look at my submission for the actual calculations that go along with that. Okay, so finally, I'm going to demonstrate this FSM. Let me set this up real quick. I'll be right back. Okay, so we're back for the final task. And in this task, I'm not going to go through the whole thing because I'm sure you already know what it does. But what we were tasked with doing is creating this FSM for our microcontroller. And this FSM is simulating an FSM that could help the servo motor. And in this case, we're pretending to be a car, and the car is either going to turn to the left 90 degrees, to the right 90 degrees. It's going to keep going straight, or it's going to stop, depending on whether it detects a car from the left or the right, or both. And we're using these two buttons that I have set up here. They're kind of where the traffic lights buttons used to be, or where they are. But they're not controlling a traffic light this time. They're just controlling our motor. But again, we're not actually going to use a motor. So what I will do though is I'll show you the duty cycles in logic, but then I also have Minicom open here that will tell us what position we're in depending on what sensors were detected. So let me actually move this to my logic screen. Okay, so let me reset this. Okay, we're already, it just keeps playing center position because center, no cars have been detected. Imagine we're going straight on the highway, just like that. Now I'm gonna hit this button and we're in the left position. Okay? And then I'm gonna hit this button and we're in the right position. And then if I hit both, we're gonna stop. But I'm not gonna do stop yet because I want to show you on logic first that duty cycles are correct. So as you can see, I already have some examples over here, but I'm going to start over. So this is the center position, and the duty cycle is, let's take a look. Oh, I'm not going to get the duty cycle on here, never mind. You'll see that the duty cycle is, I believe it's about 7.5%. Okay, and then now I'm going to hit the left button, and we're going to see what happens. And as you can see, it actually went down. It's hard to see, but here, let me do it again. Okay, that's center, and I'm holding the left button, and that's left. So it's a little smaller. I know it's hard to see, but this one is about 5% duty cycle. Okay, and then I'm going to do the right now. This one should be easier to see because we're actually growing in size. Oh, it kind of is still hard to see, but it's about 10% duty cycle. But of course, Minicom is also backing me up here. And then, let's see, if I hold both, we're just gonna stop. The car is done. Don't do anything. So that is pretty much it for that demonstration. I'm gonna pause real quick. Okay, I'm back. So I was thinking, I was like, yeah, I know there's a way to get the duty cycle in logic, and there totally is. I just totally forgot about it. So here we are. I'm gonna do this one more time. So, okay, we're in the stop position. Hold on, let me reset. Okay. So now we're in the center position, and I'm just gonna take a quick measurement, and I'll show you that the duty cycles are indeed correct. So, okay, there's that. I'm gonna add duty cycle. I mean, you have 7.496. That's about 7.5. So yes, as I said, the duty cycle should be 7.5. Okay, now I'm going to run, and I'm going to hold the left button. So let me go back to about right here. I'm going to measure the duty cycle here. I wish I would maintain it the whole time. I'm still getting used to this program. Okay, so now we have 4.9%, which is almost 5, very close to 5. So that's pretty great. I'm going to hit play again, and I'm going to hold the right button and hit stop. Measure. There we go. And 9.910. And then finally, I mean, I think you already know what this is a 0% duty cycle. Okay, so that's it for this lab. That will conclude the demonstrations. Yeah, so of course, always refer to my submission if you have any questions, but that should be it. So thank you.